So, hello everybody. I want to announce the opening talk of our meeting by Katarzyna Sznajd-Weron from Wroclaw University that is going to talk us about private truth and public lies. So when you want to start, you can start.
Yeah. Thank you very much, Celia. Thank you for organizing this meeting. I'm sure it will be a wonderful meeting. And thank you to all organizers to organize this. And I'm really, really happy to have this opportunity to open scientific part of this meeting. So I will start today with a question. And the question is the following one. So first, imagine such a situation that your supervisor invites you to the party at her home. And this home was just newly renovated. She is very proud of this renovation. And she asks you, how do you like it? You look around and the look does not appeal to you. You don't like it very much. So what would you answer? So most of the people probably would answer like, oh, okay, it's nice, sophisticated taste, or something like this. This example was inspired by this book. In fact, almost exactly this example is presented in the first chapter of this book. And also the title of my talk, The Private Truth and Public Lies, came from this book. So we've been working on this subject for already some time ago. So already in 2018 with my former PhD student and my master's student at that time, and also with our colleague Paul Nail, who is experimental social psychologist. And we published even a paper on this subject, but then we gave up somehow. And just last year, I discovered this book and I realized that the subject was really important. So we went back to this research and we continue this research right now under this project, which is also in collaboration with social psychologists. So as you see, the first part of the title of the book is The Private Truth, Public Lies, but the second one is the social consequences of the preference falsification. So what is the preference falsification? This is the concept, the idea that was introduced in this book by Timur Kuran. And it means, as you may expect, it means that you just act or you verbalize your opinion, which is not your truth opinion, which is not your truth preference. The main reason for this is that usually we believe that what we express is more acceptable socially. So as you may imagine, it has really huge social and political consequences. So to model this, you need opinions on two levels, the public and the private one. And the concept to have opinions on two levels is not a new one. It appears, for example, in the CODA model. Well, I mean, it appears in many models, but probably one of the most famous one is the CODA model proposed by Andre Martins, who is, by the way, also our speaker. But in the CODA model, you have continuous opinions, like internal continuous opinions that measure the level of confidence. And then the public opinion or the action that you take follows your internal continuous opinion. In this research, when we want to model this preference falsification issue, we need to have two opinions, but in a sense, independence. They will be not independent, but you may express something completely different from your internal opinion. So this will be our model, and for this we will need two opinions. And in our model we use very simple settings. So we will have binary variables. So each agent will be described by two opinions: the public opinion, which will take two values, and the private one, which will also take two values. And we will represent this opinion by this sign. So like so this darker one stands for the public opinion, and the lighter one in the back is for the private opinion. And the assumption, which is the heuristic assumption, is that others can see only the public opinion. So this is the first assumption, the heuristic one. Now we assume that there are only two types of responses. And this is not very realistic, but this is how we did in our first paper. So we take into account only independence and conformity. And these two types of social response comes into the model with complementary probabilities. The novelty which appears in this model is that conformity can take one of two forms. So we consider so-called compliance, and we consider also something which is a bit exotic, and it is called this inhibitory contagion. So what is compliance? Compliance is a type of conformity that we usually take into account in our models. We've been working on the Q-voter model proposed by Castellano and others for some time already, and we usually took into account compliance. What is compliance? Compliance is that you publicly conform to others, but without private acceptance. And there are many social experiments that confirm that this type of conformity is influenced by the size of the group and by the majority, I mean, how strong the majority is. So for example, if you consider only a small group of influence, like here on this picture, you know that this type of conformity increases with the size of the group up to the certain threshold. That's the one thing. So one person, maybe it's not enough to convince you. And also the second thing that was discovered in this type of experiments, that unanimity is really crucial. So if you have unanimous majority, you conform much more often than if you have at least one ally. So so the size of the group is important, and conforming increases with the size of the group, and then the unanimity is crucial. So so this we will take into account modeling compliance, and this is in fact what is present in the Q-voter model, which I will talk about today also. But the second part, the second type of conformity is something which is maybe more exotic, maybe less, but I didn't know at least that it is called like this, that the Paul name, our colleague who is a psychologist, told us that there is something like contagious conformity. And it appears if you are in your internal conflict. So imagine again the following situation. You are on the party, music starts to play, you would like to dance, but you are shy, so you don't dance. But then a single person enters the floor, starts to dance, and you are so happy, you join the person, and in several minutes or maybe several moments, the floor is occupied by dancing people. This is a very nice example by Paul Nail that appears in our paper. So I like this example a lot. So as you see, if you are in your internal conflict, so you would like to do something, but you are not doing this, or you would like to express something, but you are not expressing this, then even a single person can influence you. And then the model, like the linear voting model, would be also okay. So now, what is the model? I start with the first version of this model, which we called act then think model, which means that first we will update public opinion and then the private one. So we have our agents that sit on some given graph. The graph, this is arbitrary graph, in fact, just undirected graph without self loops, but otherwise the structure can be almost any. And then in a single update, you choose one voter at random. So let's imagine that we have chosen this guy in the yellow circle, and you update the public opinion. So first we have this independence that comes with probability P. So in case of independence, what you do with your public opinion, you change your, you replace your public opinion by the private one, which is also quite realistic. So in this case, you would change your public opinion into the green one, like your private one. But now let's imagine that maybe independence did not work. With complementary probability, conformity can happen. So what's happening in case of conformity? In case of conformity, you pick randomly Q neighbors without repetition. And this is like we do usually in the Q-voter model. In original Q-voter model, repetitions were possible, but then at least when we were working, we were choosing randomly neighbors without repetitions. So let's imagine that in this example, Q is equal to, Q is the parameter of the model, and you choose among all neighbors of this agent in the yellow circle. So in total, this agent has, like, as you see, 4 neighbors. So this guy, this guy, this guy, and this guy are linked directly. If they are linked directly, we call it neighbor. But randomly, these 2 guys were chosen. So now we ask, is my opinion, internal and the public one, equal or not? If not, it means that maybe I will be sensitive to this inhibitory contagion. And in this case, as you see, my public opinion is not the same one as my private one. So in such a case, if at least one of my chosen neighbor has the same public opinion as my private one, because I cannot see the private opinion of my neighbors, I will change my public opinion to the private one. So as you see here, this guy has public green opinion, and my internal opinion is also green. So in this case, I will change into green. But now imagine that maybe in the next time step, I'm choosing such a guy, this guy. This guy is not in the internal conflict. So how the conformity would work in this case? In this case, because I'm not in the internal conflict, still compliance can work. So I will be not convinced internally, but publicly I will express what is expressed by my neighbors. But in this case, I need unanimous group. So because in this example, Q is equal to, so I've chosen only 3 guys. But in fact, as you see in this example that I drawn here, all neighbors has expressed red. So even if Q would be 4, I would be convinced. But okay, in this example, I have chosen these 2 guys. They are red, both are red. So this guy will change public opinion into red. So this was the first thing. So how the public opinion is updated. Now I have the second part of the algorithm. So I have to update my private opinion. And the private opinion in this model is updated exactly like in the Q-voter model, which was introduced in 2009 by Castellano and others. So it means that, in fact, it's a bit reformulated version of the Q-voter model, which we've been working on for some time already, like almost 10 years. Anyway, how it works. So now for the private opinion, again, we have independence, but now independence means that I can change my internal opinion with some probability to the opposite one. So this is independence. Then we have conformity with complementary probability. And for conformity, again, we pick up Q neighbors without repetitions, and they need to be unanimous in order to change our opinion. So this is how it works. Now you may ask yourself, or even me, maybe I don't see chat yet, but you can ask why I'm doing this in this way. Why I'm updating first my public, then the private opinion. Maybe it should be vice versa. And in fact, it's not that obvious how it should be. So if you look to the textbook, I'm presenting here one of my favorite, or maybe my favorite textbook, probably my favorite textbook in social psychology by David Mayers. So if you look to this book, but if you look to others, you will find out almost the same. You will find out that it's very far from being clear how it should be updated. So you will find the sentences like this. It is true that sometimes we stand up for what we believe, but it's also true that we come to believe in what we stand up for. Then you will find out these titles like saying becomes believing. So in the end, if you summarize this, and it was summarized nicely by David Mayers in this textbook, is that if social psychology has taught us anything during last 25 years, is that we are likely not only to think ourselves into a way of acting, but also to act ourselves into a way of thinking. So it's not obvious at all what should be updated first. Should we update first the private or the public opinion? And because we didn't know how to do this, we decided to investigate two versions of the same model. They are exactly the same. The only difference is that the act then think model is how I presented to you. So we choose first one voter at random, then we make the first stage, which is we update the public opinion, then we make a second stage, which means that we update the private opinion. And we have second version of the model. And in the second version of the model, we have almost exactly the same. We only replace these two parts. So we again choose one voter at random in each update, but then we first update the private opinion and then we update the public one. So this is the only difference. So we made these two models. What we do, we measure in this model. So first, of course, we measure something which could be measured, in fact, in social pools. So we measure the fraction of positive public opinion. So how many people express positive opinion, yes, agree, or something like this. So we look at all these guys. We are interested only in the public opinion. So this is what we measure. We can measure also, because we are making just a model, so we are able to measure it. It would be not so easy from the experimental point of view of social scientists, but in the model we can do it. So we measure also the fraction of individual with positive private opinions. So now we are interested in all these guys that have private positive opinion. And then we measure something which is extremely important from the social point of view. We measure the level of dissonance. So we measure the fraction of individuals that have different opinions on the private and on the public level. So as you see, these guys, they have exactly the same private and public opinions. So the level of dissonance of these guys is does not exist. And this will give you 1. And these guys are in dissonance. So in the end, this is a good measure for the dissonance because it takes value equals 0 if everybody is in an internal harmony, and it takes value equal 1 if everybody is has different public and private opinion. So what we obtain from this? We first started with the complete graph, and this is what we have done in our original paper. So here you see outcomes of Monte Carlo simulation, as well as analytical calculations, because for the complete graph it is very simple. It is just the mean field approach. So this gray line, solid gray line, is the outcome of mean field approach, and symbols stands for Monte Carlo simulations. And as you see, no matter which model I choose, think or act and think, they overlap completely. So they give us completely the same result. And the same is seen for the public opinion, because in the upper row you have public opinion, the concentration of public opinion, as well as concentration for the private opinion. There are several interesting things here. So the first thing, which is expected maybe, but interesting already, that although the transition point for the private and for the public one is at the same place, as you see, the level of majority for the public opinion is much higher. It's higher than for the private one. This is the one thing. The second thing, which is really surprising, that from both models you obtain exactly the same results. And the third thing, which is maybe not so obvious for everyone, but for us it was obvious because we've been working on these models for some time already, that for some value of Q, the Q is the size of the group of influence, you switch from the continuous to discontinuous phase transition. Okay, so this is the result. For the public and the private opinion, you see that the order in which we update this opinion does not matter at all. But if you look at the stationary behavior of the dissonance, you see there is a huge difference between think and act, or then act, or act and think model. Again, with solid lines, we denoted outcome of analytical calculations, and with symbols Monte Carlo results. So as you see, they overlap, and we see the huge difference. So like for think and act model, the dissonance is really low, and it drops down with P, at least in this part. So you see already the huge difference. Now when we went back to this research, we asked ourselves, okay, but maybe this difference is not visible for the complete graph, but maybe it will be visible for more realistic, let's say, structures. So we decided to simulate the model on Barabasi-Albert network, on Watt-Strogatz network, and many other graphs. And what we found out is that even if you take Watt-Strogatz network with not very high connectivity and with relatively small beta, which means that the clustering coefficient is relatively high, the difference between these two approaches is not really huge. You see some difference now, but it's not really huge. And now, again, some of you may think, okay, but again, this model is a bit strange because we assume that we can behave like conformist or independent person with some probability. Maybe we should assume that some of people are conformist forever and some others are independent forever. So instead of having the same probability P of being independent for all people, we should have some people that will be permanently independent and some fraction, permanently independent, which are here, or permanently conformist, which are here. And we can do this, of course. So we did it recently, and what we obtained is that now it's even worse. I mean, again, no matter if we take act and think model or think and act, results are exactly the same. But now, as you look at the dissonance, the difference is even larger. So so it's, I mean, again, from the level of opinions, you don't see the difference between models, but from the level of dissonance, you see the huge difference. So summarizing this, looking just at the opinion, you don't see any difference. The critical point is the same. The private level is a bit lower, but it's not a huge difference. But if you look at the dissonance, you see that the difference between these two models is the huge one. And the dissonance is something which is, of course, not really nice. So my take-home message from this lecture is, it's okay to follow the crowd. It's okay to conform. In fact, it's really good to conform sometime, but you should think first. Thank you very much. And now I can look at the chat if there are any questions. Okay, and I see there are some questions. Does maybe some of you would like to ask question just like yourself, or should I write? Should I read?
Felipe?
I can ask myself.
Yeah.
Can you hear me? All
yeah.
right.
Yeah.
I was asking, when you gave the example about the house decoration, right? The respondent had to decide whether to lie or to tell the truth. I was wondering, this is a situation that happens very rarely. It doesn't seem the type of situation that you can have a bunch of agents discussing whether they're going to lie or to tell the truth. So I imagine that you have to carry from previous experiences whether how you decide whether to lie or to tell the truth, right?
Mm-hmm.
Whether to express your correct opinion or your internal opinion or to lie in public opinion. And I want to know how does this model incorporates this possibility of carrying information from previous interactions and different situations from others into this example that you gave before.
Yeah, thank you for this question. This is a very good question, and indeed, as probably some of you noticed, this is completely these agents are completely memoryless. Like they even don't remember the one step back opinion, which is really bad and really not realistic. So of course, to model what you are propose, and in fact this is really important, you have to introduce memory into the model. In fact, we did this not to this model, to the model with only one level of opinion. As I told you, we gave up with this model, and now we are back, and we are trying to like fix some unrealistic features of this model. And one of this feature for sure is memory, because also we don't like to be in internal dissonance. So there is cognitive dissonance, which is really strong force in social science. So we have some ideas how to solve it, but in this model we don't have it. So in this model we don't have any memory. So thank you for this. Thank you for this question, and for sure it's really important. Okay, so I see another question, several questions. So the second is from Marcos. Do you like to ask your question yourself, or I can? So the question was how graph structure influences dynamics. Have you considered a model with two simultaneous graph structure, private and the public ones? So this is again very good question. We were working on multi-level graphs, again, not with this model. So in this model, there is exactly the same structure for the private and for the public opinion. But you are right that probably if you think about private opinions, we should take more into account our first, let's say, social circle, like our really close friends, or our parents, for example, or our kids, or whatever. So for sure, it would be really interesting, but we didn't try it yet. So so this is really a good idea. We've been trying with the Q-voter model on multi-layer networks, but only with a single opinion, not with these two levels of opinion. Now we have another question. Maybe I can quickly ask, and this will be the last question I can answer. Sorry. Can this model give us insight into a political system that practices democratic centralism? Yeah, that is our hope. I mean, this is why we in fact started to work again on this model. I cannot answer you yet how can we help to solve some problems, and how can we understand some phenomena, like, for example, social hysteresis. This is in fact the subject of my grant. I'm working right now on this. So the only thing we see that taking it into account the private opinions, we see that, for example, the social hysteresis appears like more likely, let's say, like in short. So so what we see in real social systems, that sometimes we see the social hysteresis, so like going out from the crisis takes a long time and so on. It can be understood better if you take into account this private opinion. The problem is that it is not that easy to measure this private opinion, but this is in fact what we are thinking now with our colleagues. So for sure, I mean, this is our motivation, but I cannot give you the answer yet. So I think I consumed all my time. I stopped share the screen. Thank you again a lot for all your questions, and I yeah, I'm sharing the screen to Maxi.
Thank you very much, Katarzyna, for your nice talk. So, Maxi, can you share the screen? And I can already announce the next talk by Maxi San Miguel from IFISC in Palma de Mallorca, Spain, who is going to talk us about coevolution dynamics of opinion and social network.
Thanks very much, Celia, and thanks for the invitation to participate in this workshop. What I will discuss is work done in collaboration with a postdoc here, Megdad Sadian, and with my friend and colleague, Raúl Toral. And it is essentially contained in these two references. Now, the first question is, what do I mean by coevolution in the context of opinion formation or opinion dynamics? Now, generally, we set up a model of opinion dynamics with agents, which are nodes in a network of interactions. Then I restrict myself to the simplest case in which the state of the node, which is an opinion, is binary. It's just say blue and red here. But now we have the characteristics of the link in the network. This link, the first thing is if it exists or not. This is given by the Eddy-Smith matrix. Then it can be weighted. But then we can also have a state of the link, which can be the type of interaction. It can be homophilic or heterophilic or other things. So given this setup, one can distinguish three different steps in which what we consider by coevolution. The first one is one in which we do not give any state to the links. They just exist or not exist, but the links are not persistent. And then we have a couple dynamics of the state of the nodes, the opinion, and the topology of the network. A second step would be consider a fixed network. The network does not evolve in time, but we have a couple dynamics of the node states and link states. And the third step, which is the one that I want to talk about today, is in which the nodes have states, the links have states, and the topology of the network is evolving. It is dynamic. Now, before going into this third step, let me very briefly remind you of this first step, which is the context for this type of work. Now, when we talk about the dynamics of the network, usually we can talk about the dynamics of the network formation, which is the structure created by the individual choices or actions, or the dynamics on the network. The network is fixed, does not evolve, but actions of individuals are constrained by the social network. When we talk about coevolution of agents and network, is when the state of the agents is evolving coupled to the dynamics of the network. And this is part of the research agenda that Michael Macy established in 1991, saying that it's a new research agenda in which the structure of the network is no longer a given, but a variable, and see how the social structure evolves in tandem with the collective action. Now, what is the final goal of this type of work is the understanding of process of group formation or social differentiation, but especially in opinion dynamics, the emergence or polarization or an echo chambers. Polarization is here understood as situations in which the distribution of opinions in the population is characterized by two similar peaks associated with the two opinions. But here there is no implication on the topology of the social network. While when we talk about echo chambers, refer to situations in which one's opinions resonates with those of one social context. Therefore, it is topology dependent, and it is polarization together with these echo chambers which give rise to what is called normally a majority illusion in social networks. So in this coevolution problem, this step one, we can do that in terms of the very famous Bolter model in a network in which ties are not persistent. Now, the Bolter model implements the mechanism of social imitation, in which what we have is one agent that looks at a random neighbor and copies the state of the neighbor. But there can be also breaking and establishing new ties. That's rewiring, that's dynamics of the network. So we have this situation, I look at one of my neighbors and I can do two things, just copy, which is changing the state, or breaking this link and establishing a new one in the network, rewiring. It is the competition between imitation or choosing neighbors. Now, what normally happens is that this combination of imitation and choosing neighbors gives rise to a network fragmentation transition. When imitation dominates over rewiring, the system converges to a single opinion in a single component network. While when this rewiring dominates, the network fragments into groups of different opinions. Now, this fragmentation is due to a competition of the time scales, the time scale of evolution of the state of the node and the time state of evolution of the network. And this parameter is called plasticity. Okay, you have details of the mathematics of that in this relatively old paper, but that was to set the state of this coevolution in the simplest case, which I call the step one. Here you have a reference of this thing I call step two, and let me go to this step three, which is the coupled dynamics of states of the nodes, the states of the links, and the topology of the network, which is also evolving. So the model is constructed in this way. We have nodes that can be in either of two states, and then we also have link states. The interaction can be positive or homophilic or negative or heterophilic. Now this gives rise to 6 different pair relations, which we call, or that we classify in satisfying or unsatisfying. A satisfying relation is when two nodes have the same opinion and have a friendly relation, like this 1B or like this 1D. It is also satisfying if we have a different opinion and our relation is heterophilic or negative, while the 3 other relations are unsatisfying. For instance, having the same opinion and a heterophilic or negative relation. Now, the dynamics of the model is evolving towards satisfaction. Evolving towards satisfaction means that these unsatisfying pair relations evolve to satisfying pair relations. And this happens in 2 different ways. Take this unsatisfying node, and it can be evolved into a satisfying one by 2 mechanisms. One that occurs with probability P, which is change the link state from unsatisfying to unsatisfying, and with complementary probability, what we do is we change the state of the node. The same for this unsatisfying relation, that either we change the state of the node or we change the state of the link. Now, for this particular relation here, we again can become satisfying by changing the state of the node in this direction and this direction. But once we have selected the with probability P to update the link, this link can be updated in 2 ways: by changing the state of the link, or with probability R by rewiring, so that I go to another satisfying link. So this thing can evolve by changing the state of one of the nodes, or by changing the link, either by changing the state of the link or by rewiring and given dynamics in the network. We could also think that these pairs could change by rewiring, but this is one can argue socially that this is less probable, because it would mean going around searching to establish a friendly relation with an agent no, let me say it correctly. It would be much less improbable that we rewire here. That means to break an unsatisfying relation to establish a different type by relation by satisfying. Okay. Now, this is just a reminder of the dynamics, and we implement that in a random network with mean degree, mu. Those are the parameters. And which are the variables? The variables are the link densities of these 6 quantities. Now, an absorbing state of the dynamics is when there are no unsatisfying pairs. So when the density of these 3 links goes to 0. Now, what we find is an absorbing transition from a state which is dynamically active, so it doesn't reach a global satisfying state, to an absorbing frozen configuration. This can be done in a rate equation analysis in the thermodynamic limit. So in the dynamically active state, these 6 link densities are non-vanishing, and in fact they all can be expressed as function of this rho sub e. In the particular case r equal 1, r equal 1 means that this link only changes by rewinding, not by changing the state of the link. Then in this dynamically active state, there are no negative. In the absorbing frozen state is when the densities of these 3 links goes to 0. And one can calculate the absorbing transition line in this rate equation. Now, how does this compare with numerics? What I'm showing you is identify the transition point by the density of this link going to 0. And I'm showing here as a function of the mean degree or as a function of the probability with which we change the state of the node. I remember that is, excuse me, when the probability in which we change the state of the link, P. Okay, as you see, with those are for different values of this rewiring parameter R. In continuous line are the rate equations, and dashed lines are the simulations. The transition is well identified, but in the simulations, this transition point does not depend on the rewiring, which is a wrong prediction of the rate equations. What I'm showing here is in this parameter P, the probability of changing the state of the link, and mean degree of the node. In the transition line, in this absorbing transition, calculated by theory is the continuous line, and calculating and by simulation is this dashed line. So there is a transition which is well identified. What I'm plotting here in a color scale is the density of this link rho sub f, to show that this really depends on the rewiring rate, and in fact, when it becomes 0 in the active zone for this density equal to 1. So if the transition is essentially independent of this rewiring, why this rewiring is important? Well, this rewiring is important in the dynamics and in the final configurations. Of course, in the active phase, finite size fluctuations take always the system to an absorbing state. And what happens is that when there is no rewiring, this goes with a time that grows exponentially with n, while in the presence of rewiring, it goes linearly with n. So the rewiring, what it does is reduces exponentially the lifetime of the active unsatisfying state. Because after all, these unsatisfying states will, because finite size fluctuations, convert to a satisfying state, and it will be much faster in the case of rewiring. But we have identified a transition then from an unsatisfying active state to a satisfying frozen configuration. But in finite systems, the active state has a final lifetime. Finally, we always end up in a frozen, satisfying configuration. The question is, which are these possible configurations and where do we find? Okay. As I said, this is the final, in a final satisfactory state, these 3 densities will be 0. This is a reminder of which are these densities. Which final state do we find? First, there is this fragmented state in which we have 2 groups. I mean, one group in which all the nodes have one given opinion and they are linked by positive relations, and the other group with the opposite opinion and with positive relations. And there are no negative or heterophilic links present at the end. Now, this is this fragmented configuration, but we also have final connected configurations. The first one is the consensus configuration, in which all the nodes are in the same state and connected with positive links. What I draw here is that this is reached by finite size fluctuations. So during some time, it will. This is a snapshot of the dynamically active state that will finish here. Then we have what we call two-group or split configurations. What is a two-group? We define a group as here as a set of nodes in the same state, here Y, connected by attractive links among themselves and by repulsive links to the nodes of the other groups. In a two-group configuration like this one, there are only two groups of nodes, each group in a different state, and the two groups connected by some repulsive links, while the internal links in each group are attractive. The split configurations, what happens is that some very small groups are attached to the two large groups by some repulsive. But in either of these two configurations, we don't have this, or we do have this type of links, ρF, here, which connect nodes in different states with a satisfying relation. Now, how they are found in our parameter space? Just a remain. I will start looking at the case in which this link here only evolves by rewiring the node. It is not by changing the state of the node. And in this case, there are no negative links in the active state. And the density of these other links, which is zero in the active state. So, no links in the final state of this type here. What I'm plotting here in the parameter space P and mu is the degree of the network, and P is the probability which we find in which we change the state of the link and not the state of the node. Okay, we see that the fragmentation only occurs at this line, which is the line of the absorbing transition, while the consensus configuration only appears in what in the thermodynamic limit is the active, the dynamically active state. So that fragmentation only appears as a manifestation of criticality, only appears in this critical line. Now, what other configurations appear here and here in this black area? This is where the two group configurations occur. This, what I'm plotting in the color scale, is the probability of finding this configuration. This probability of finding two group occurs here, and this split configuration appears. So in a sketch, this is the summary of what happens in the final state. Parameter space is the degree of the network, and P is this probability of changing the state of the link. Fragmentation only occurs at the critical line. Consensus is what appears in the area which in the thermodynamic limit is active. And these two group configurations only appears for a connectivity beyond this critical one, which means that these two group configurations, which are, if you want, a paradigm of what we see as an echo chamber situation, only occurs for large enough connectivity. Okay, what happens in the case in which this rewiring is not one, in which this link can also change by changing the state of the link? What I'm plotting here or showing you again, in this parameter space of this probability of changing state of the link versus the degree of the network, are the probabilities in current scale of finding consensus, two-group or split configurations. So here is the sketch of what we observe. Here there is this green line, okay? So here we have two-group configurations, split and consensus. What is different from what we find for R equal 1? Well, first thing is that there is no fragmented state. We never find the fragmented state. Second is this green line here is moving to the right as the rewiring probability decreases. So that there is no consensus phase, this thing disappears when there is no rewiring. And next, this finite size topological transition from the split configuration to the two-group configuration moves to the right when decreasing the rewiring. This is shown here. What I'm plotting here is the probability of finding two groups as the histogram, as the number of groups, for different values of the network connectivity. What you see in this graph is one that the rewiring is rather large. This critical value of the connectivity goes from 9 to 10. That's when there are only two groups. While when there is no rewiring, this goes to the order of 22, much larger. So this is the technical results, and I'll now try to summarize to see what all that means. Okay, so we found, or what have we learned? I've presented the general co-evolving model with two parameters, and this is the phase diagram. Here is the degree of the network, and the two parameters are P, which is the rate of change of link state versus node state, and R, which is the rewiring. Okay, what we find is a transition in the very large limit from an active unsatisfying situation to a frozen satisfying situation. What do we know about these two parameters, P and R? Well, to obtain a satisfactory final configuration, P has to be large enough. So it is better to change the state of the link than to change the state of the node. And even when you end in an unsatisfying relation for a long time, if you increase the rewiring, you will much earlier end up in the final satisfactory configuration. So conclusion is that the global satisfaction is promoted by fast range of the change of link state and by rewiring. So the relevant dynamics is not the dynamics of the node, but the dynamics of the network, either changing the state of the links or changing the presence of the links. Now, going to the final configuration, and this is where we can make some social interpretations, what have we found? These social polarization and echo chambers are these two-group or fragmentation situation. It's a typical situation of echo chamber, polarization, but with topology dependent. Now, this happens beyond this critical value of the connectivity. So for this to happen, we need large connectivity. We need globalization. And a smaller connectivity is needed in adaptive networks. So the existence of this echo chamber type of situations is promoted by globalization. On the other hand, to arrive to this type of situation, we need these heterophilic interactions to remain. So heterophilic interactions, the negative interactions, promote polarization, because when there are no heterophilic interactions, we end up in consensus or in the fragmentation, but fragmentation only occurs in that line. is a very special situation, a manifestation of criticality. And finally, consensus is only possible with rewiring. If there is no rewiring, if there is no dynamics of the network, we never reach this consensus situation. So to reach consensus needs positive satisfactory relations that appear opting out of disagreement with our positive relations. And I think this is the summary of what I wanted to tell you. And I'll now leave my sharing the screen. And then I see that here there are a number of questions that I might try to answer. Or Celia, do you want to do it other ways?
Let me see. I think the first is
well, there is a question here.
Pratyush Kumar, can you ask the question? Sorry, it's not the first. Sorry. It's Rassier. The question is if you change the network topology, for instance, if you use scale-free networks, what will happen with the transition?
Yeah, the network topology is not fixed. It evolves in time. So typically, even if you start at the very beginning with a scale-free topology, you will evolve into a random network. So we haven't checked that carefully, but my experience with other problems of coevolution is that you might start with different types of networks, of course, unless you choose a pathological one. But since the network is evolving due to all these mechanisms, you end up in some type of random network.
Thank you. There is another question by Pablo Valenzuela. Do you want to ask yourself, Pablo, or me to read?
Yes, I can ask. Hello, Maxi, very nice talk. I would like to ask you what happened if opinions were continuous? Because I'm interested in final states related with echo chambers. And from the hypothesis of your model, I understand that in a two-state opinion model, you have the opinions are already polarized. And you also add homophilic and heterophilic interaction. But do you think that this is possible to obtain an echo chamber-like final state with a model of continuous opinion? And which aspect of the dynamic do you think could be relevant in that case?
Well, this is an interesting question. We have not looked at that in detail. But if I have to make some hypothesis or assumption, I think in terms of echo chambers, what would be interesting to see is that you start with some type of continuous opinion, but by the end of the dynamics, you end up in two groups in which each group has gone to one of the two extreme opinions, and that could happen. But I don't know. We have not done that. We've just started with this simple case in which you have two of these opinions, and the question is, well, when states with these two opinions survive, and this or when do you finally reach these all different configurations that have been described? So I think this is an interesting question, but I cannot give you an answer more than some wishful thinking about it.
Thank you, Maxi.
Thank you. There is another question by Felipe. Felipe, do you want to comment?
Yes, sure. Does this rewiring of the network requires modeling beyond opinion, the behaviors beyond opinions, say trust or other kind of relations between agents?
Well, I mean, there are, as you know, in these models, one can implement many different mechanisms. The basic idea here is that you have a relation which is unsatisfactory because and you see how you want to go to a satisfactory relation. And what it is implemented here is that instead, this rewiring means a possibility, which is instead of changing the state of one node, or instead of changing the state of the link, what I do is I break this link and establish a new link such that the new pair relation is satisfactory. And that's it. That's what we do. And of course, the question is, well, how the final states depend on these different parameters, especially this rewiring parameter R. This rewiring parameter R is once you have chosen a link to be updated to become the pairwise relation satisfactory, instead of changing the state of the link, you rewire. That means you do a change in the topology of the network.
George, may I rephrase that? What I mean is this rewiring represents something that humans do. Like we update our opinions when we interact with others. And now there is this new mechanism in the model that is to rewire the social connectivity. And I wonder if this is connected to something that we also give a name, like we give a name to opinions. That's
okay,
what
well, in what I call the step one, which was the simplest case, I made the difference between imitating our neighbor or choosing neighbors. So this rewiring mechanism is the idea of choosing in new relations. I mean, right. If I don't agree with someone in which I'm all the time interacting, well, finally I may say I forget about this relation and I choose a new neighbor. I look for another relation.
Oh, all right, thank you.
Okay, thank you very much, Maxi. We are going to have a break now, a 15 minutes break. I want to make this announcement. If there are more questions, you know that you can go on by Slack, enter Slack, where we create different channels if necessary. But I think it's better if you ask to everybody, open to everybody. Two announcements, so I will try to share my screen now. Rapid announcements of events. Can you see the screen? One of the events is from this institute. You can take note of these usual webinars, but in particular today, after our meeting, there will be a talk about reservoir computing, very interesting subject. So Hilda, I don't know if you want to comment something, but Hilda Cerdeira, who is from the ICTP-SAIFR, will put in our chat the link for the event for those who are interested. Okay, Hilda?
Hello, thank you. Thank you, Celia. First, I have to apologize because this is really a mistake on my part. We should have been more careful with the timing of and change most probably our seminars. But anyway, that's how it is now. So I have put already the seminar is going to be about reservoir computing, and I want to call your attention because we have asked the speaker to give a good explanation on this subject, which you can see nowadays more and more in the literature. And as I say, before the explanation disappears, because they assume that everybody knows it. So then we want that's why I want to call especially to this attention. I am also sending, apart from the ID and password for the Zoom session, I am asking Humberto, the secretary of the conference, to distribute this email that is on your screen to everybody to all participants and speakers. So thank you very much for giving me the opportunity to show this, and I apologize again.
Oh, thank you to you, Hilda.